Hi. Today's topic is subexponential lower bounds for f-ergodic Markov processes, and that is based on very recent work with Miha Bresar, who is a postdoc at Warwick. I'll make two videos about this. This one I'll discuss the results, and then the next part two I will discuss the proof of our main theorem. Okay. Now, the motivating example is this situation where you look at an ergodic elliptic diffusion in Rn that has heavy-tailed stationary distribution. Now, one makes some asymptotic assumptions on the coefficients, and in particular the heavy tailness of the stationary distribution is seen here in the drift. You see the drift, of course, has negative sign at rate alpha, but it is sublinear. You see L, the parameter L is smaller than 2. It's sublinear. This will read the heavy tails, as long as the dispersion matrix is such that the instantaneous variance is also of the right exponential order. You don't want to wild fluctuations. Okay. In that case, Ford and Roberts proved in 2005 that X is indeed ergodic and has stationary measured pi, and that the convergence, so the distance, the total variation distance between pi and the marginal, decays polynomially. And if you look closer at this coefficient here, this power here, you notice that it can be arbitrarily close to 0, right? So it's going to be positive, so it's going to be negative, but just a little bit negative, right? So the question really is, what about a lower bound? Does this really decay so slowly or not? So can we find a lower bound that is of the same order? So this is my main topic, and in order to tell you about our work that does this, I need to first recall how upper bounds work, and then move on to lower bounds. Okay. Now, upper bounds, this is this super successful theory of Lyapunov drift condition that's been around for many decades. What does it say? Well, it says that if X is irreducible Markov process, so goes everywhere in some locally compact state space, then what I need to really do in order to understand its convergence to stationarity and whether it is stationary, I need to find a Lyapunov function, so a function that sort of maps the problem to a one-dimensional half-line. And then I really need to consider this process V of X. And this process should be a super martingale itself. But in order to get quantitative information in the upper bounds and the tails, I need more, right? I need another scalar function phi, which is increasing and concave, such that when I add this function, this process is still a super martingale. You see, super martingale drifts downwards, of course. And if I add a little bit, it will still drift downwards. So I need a bound under drift. I'm sort of ignoring this guy here because this A will typically be compact, and you won't see it because I'm interested in the process when it's out in the tails. Okay? So if I have such a V and such a psi, then mine and Tweedy's sort of classical results by now from the early 90s say that X goes everywhere, really, has invariant measure pi, goes everywhere sufficient phi has invariant measure pi, and that this function in the drift actually is integrable with respect to pi. I don't know what pi is, but I know that this function is integrable. Okay? And moreover, it gives us asymptotic quantitative control on this total variation distance, right? So how does this control look like? So I've got this function phi, I construct this h, and then the bound is this. And now you see here, this phi is linear, actually. That's concave, right? That's extreme case. This is going to be a logarithm, so this is just going to be exponential here. So I get exponential rate. If phi is linear, I get exponential rate. But if phi is genuinely concave, then I will get subexponential rates. And this is the case I'm interested in. That's exactly where the polynomial rates from Ford and Roberts come from. Okay, we've got these polynomial rates, but how about lower bounds, right? Are these rates actually the right rate of convergence? Okay, so in order to answer these questions, what we had to do is introduce new L drift conditions, where on top of the Lyapunov function V, we also define two new scalar functions that do a job. So the first one is this phi. Okay, so I'm interested in lower bounds, right? So it's natural to look at 1 over V. Okay, this 1 over V is not going to be a super martingale, but if I can estimate the drift of 1 over V and compare it to 1 over V of X itself via this function phi, and the function phi is a function in 0, 1, okay, which goes to 0 when r goes to infinity in this context. So this drift is somehow vanishing. You see, I have to subtract less and less as when process x takes large values. then this process here will be a super martingale. So that's the first condition that I need. And the second condition is I need this function psi, which is a submultiplicative function that goes to plus infinity, okay, which controls the exit probability. So I take two levels, L and R, and I start the process between the levels L and R versus V of xt, and then I worry about this probability. How does that decay? How does the probability of the event that I exit above before going to L, how does that decay when the upper bound goes to infinity? And this needs to be bounded from below by this function psi of R. Now this looks maybe like something that's hard to check in general, but in fact this is again in disguise, in some special case, a drift condition, because all I need to do is I need to look at this psi composed of V and require this to be a submartingale. Okay, so that will imply this thing by standard arguments. Okay? But I still write it in this general case because some examples require this. Okay? You cannot always get a submartingale the way you would like. Anyway, so I've got this LV, this L drift condition depends on the Lyapunov function psi, phi and psi. Okay. Now, okay, let me show you the lower bounds that this entails, right? So I define this function, which is, this is the R phi of 1 over R, and there's the function psi of R roughly, and times some logarithmic factors and tiny epsilon. Okay. And then immediately, if this condition holds, and the process, the underlying process is positive Harris recurrent, which it will be if I have a good Lyapunov function for upper bounds, then the tail of the measure I get a lower bound on the tail of the measure in terms of this function. You see, this function is interesting. It's not immediately clear, you see, that this function goes to plus infinity, because our assumption states that R times phi of 1 over R goes to 0 as R goes to infinity. But psi actually needs to be pushing to infinity faster. So this will indeed go to plus infinity, and this will be a genuine lower bound, and as you will see, it's quite a good lower bound. It's a matching lower bound. Okay? And now, in order to go from the lower bound to the upper bound, to the lower bound on the convergence, once we obtain this, we need a function h, which sort of determines the growth rate of h is an increasing function, and it will tell me, I will use it to control the tail of the process v of xt using Markov inequality, right? So the bound by some v of xt, where t goes to plus infinity, this v will be growing to plus infinity also, and little v, and this will typically be linear, but not always importantly linear, as you will see in examples. So that's one component of the bound. Another component is that I look at the lower bound of the tail of the stationary measure, I take any function that is below it, including this boundary function, such that this goes to plus infinity. And then the lower bound is on the tail, on the total variation is given by this composition with this v and a. So a goes to plus infinity, a to the minus 1 also goes to plus infinity, v goes to plus infinity, so this goes to plus infinity. And then I compose this with little a, and this will of course go to 0 because of this restriction. So that's my theorem. Let's see how what it does in practice. Okay, go back to the original problem with polynomial tails and these asymptotic assumptions, sublinear growth and drift. And it's easy to see that these polynomial functions for psi, phi, and v fit the bill, satisfy the L drift condition, and now that I have these functions, they're explicit polynomials, I get this lower bound, which is explicit even though I don't know anything about, in general, about the pi, because of course the noise here is multiplicative. I get a lower bound of this type. And now, this is the first part of the theorem. Now the second part of the theorem, under the same assumptions, gives me a lower bound. I mean, actually, I use a theorem from the paper, not theorem that I stated, because here I'm looking at the actual f variation, right? I look at f variation, and I get this polynomial bound with this eta k. Okay, why? Well, because Ford and Roberts actually proved an upper bound in this f variation for this kind of diffusion under these assumptions, and what we see is that this theorem LB actually gives matching lower and upper bounds in this case. So maybe that's a little bit abstract. To be slightly more concrete, in the Langevin case, I take L to be 0 because there is no dispersion coefficient as the identity, and I take the drift, and the drift is sort of vanishing. For L0, the drift is vanishing at this rate. I recalculate the coefficients, and I get, again comparing with Fortin-Roberts, I get matching lower and upper bounds as one would expect. Okay, so this implies that implies the actual rate of convergence. Implies the rate of convergence, and this epsilon here, of course, this is something we can't get away from because our assumptions are asymptotic. Assumptions are asymptotic, but nevertheless, so we don't know what happens on compacts, but nevertheless, of course, the actual rate of convergence is the correct one. Okay. Now, another class of models in this context is diffusions with stretched exponential ergodicity, right? They were studied extensively in this paper by Duke et al. That I mentioned earlier. So here I allow more general coefficients more general assumptions than before, in that you see the drift is again polynomial, but allow it to oscillate between two constants. It's not, I don't have asymptotic control. In fact, in the polynomial case, I could have done the same thing. It was just for ease of exposition that I did that. So, lower bounds, typically, as you will see later, I'll mention later, in ergodic theory, you need to have very strong control on the coefficients, right? The coefficients need to be asymptotically controlled. They have to have asymptotic behavior. But here, you can allow for this oscillation. Also, in the dispersion matrix, same thing. And in this case, again, I go back to this diffusion and try to apply my theorem. So I need these functions there. Phi is here polynomial, psi is stretched exponential, it turns out, and v is just the norm. And in that case, I need to now importantly also control the growth rate of this in order to control the tail of v of xt. Here it's a very good idea to take h, also stretched exponential, and this will make superlinear growth in t, but will still bring optimal bounds, right? How do I know that the bounds are optimal? Well, as I mentioned, Duke et al., they studied these upper bounds, and we get the same rates. You see, we get the same rates, both in the measure and in the rate of convergence. Note here that in the exponents, unlike in the exponential case, there are no epsilons, because these epsilons, the compact, what happens on compact sets, actually hidden in these constants. Okay, it's hidden in these constants. There's more discussion of that in the paper, and this stuff can be said about this size of this constant discrepancy between these things under additional assumptions. Okay. Now, exponential ergodicity also works, right? So if I take p equals to L equals to 0, then this model will be exponentially ergodic. And we can, in that case, obtain exponential lower bounds, meaning that the actual convergence rate is not, super exponential or anything like that. We can identify the rate as being 1. Now, I will conclude with this final example where we have jumps. We have to do something with jumps, of course. In fact, in the paper, we also look at hypoelliptic diffusions, but I will not talk about that in this presentation. But if you have jumps, you look at an OU process, and this OU process ends up not being geometrically ergodic if the jumps are very, very heavy. Okay. So we take arbitrary pure jump Levy driver, and all that we assume is that the tail asymptotically sort of is bounded between some log r to some power mc, where mc is greater than 1. Okay, but again, we don't require limits. We require only sort of lower and upper bounds in this behavior. On the left-hand side, we can have any measure you like, as long as it doesn't have this ridiculously strong tail. On the other side, just slightly thinner tail. Of course, see, this is an extremely heavy tail. Right? And the path variation is also allowed to be arbitrary. Again, I find these functions exactly in this way. Take this h to be the polynomial. See, this kind of has to be close to integrability. You see, integrability with respect to this Levy measure. You see, r mc, see, h of v, this is logarithm to the power mc minus epsilon will just be integral with respect to the Levy measure. Okay? And this is precisely the good guy to take. And then this will make this guy grow linearly in t. It'll be fine growing linearly in t. And this psi here cannot be proved using the sub-martingale condition. I need to, this guy, remember, this psi controls the probability of exit, right? So I need to do this exit probability directly from path properties of this process. But of course, this is not difficult. Such path analysis can be done also. The bounds match those obtained in Ford and Roberts. So you see here, this is the tail, decays logarithmically the stationary measure, and our power is exactly the same. And of course, the step to the total variation also matches. Okay. To conclude, to the best of our knowledge, these are really the first general Lyapunov drift conditions that obtain lower bounds for ergodic Markov processes that cover wide class without any specifics on the model. Okay. It really is a complement and extension of the existing classical theory for Lyapunov drift conditions. You see, because we start with this Lyapunov function for the upper bounds, and then provide a test via the scalar functions phi and psi that shows whether the function is good. Right here, I must stress that the higher in his notes made this, to the best of my knowledge, made this observation first that if you have lower bounds, controlling the lower bounds in the stationary measure, and you can translate that to the convergence, lower bound convergence in total variation. So we extend that model to f variation, but more importantly, provide a general approach to obtaining lower bounds on the tails of the stationary measure, and then where this sort of idea can then be sort of given legs and applied in cases where we don't know the stationary measure itself. This was in these notes. This was applied to the case where the stationary measure was known explicitly. And now this connection with ergodic theory, of course, is very natural in this context, and these polynomial decays of correlations and mixing times have been discussed and analyzed in this famous paper, Bresar from 2002, and it's based on actually far-reaching generalization of Rogozin's idea on the error bounds on the renewal in the renewal theorem, right? So it would be natural to ask, oh, why don't you do that in the context of Markov processes? And it turns out that these restrictions in Sarig, as I was saying, the coefficients really need to be controlled asymptotically, while we can allow fluctuations in the coefficients. So if we could do this mammoth task and apply it here, we're likely to get weaker results than what we obtained. Okay, so here are the papers that I've cited, the Duke et al., Ford and Roberts, Hirig's notes, mine and Tweedy, classical stuff, and Sarig's paper on subexponential decay of correlations. And I hope this is sufficiently interesting for you to, watch the next video, which will be on the proof of the theorem LP. Thank you for your attention.